So in this course, we will be using the C programming language. And unlike other languages like Java, which has its own support at the language level for multi-threading, C will depend on library functions. And the one that we will use is the pthread library or the POSIX thread library, which has come to become a standard. How do you use pthreads? So in a standard program, C program, this is pretty much what you need to do is pound include pthread.h, set up a function that you will execute in separate threads. So you will have your main program. That's going to be where the parent process starts. Then you'll do a bunch of things to create threads. And when you, unlike Java, where you can create a thread object and then later start it, in C, when you create a thread object using pthread create, it creates all the data structures like the stack that you need for the thread to run, and then it also starts up the thread right away as soon as you create it. There are other ways you can start up threads, but this is like the standard way of that we will use in this course. Okay, so main once again is the parent. It is running in a separate process. Here what we do is we create a thread and it'll start running. We call the sort of the pointer to the struct that holds all the information about the thread P1. And then we have to give it, one of the things we have to give it is a pointer to a function. So when you declare a function, you can pass that name of the function around, and that is a function pointer. There are some conditions that you have to meet for the kinds of things that you're going to pass into the pthread create. For example, you can't have arguments like you do with normal functions. So yeah, arguments work differently. And so here we're going to pass in, it turns out we're going to create a thread to execute this function myThread. And we can create another thread to execute the same function. They're going to be separate. We're going to have two separate things. We can also pass in arguments to myThread. You don't put, if you put open close parentheses here, right here, you're just going to call this function like you would normally, and you wouldn't be multi-threading at all. So that's like a common pitfall that people who are learning about multi-threading make, is that you don't want to put open close parentheses right here, because then you're just calling the function. Instead, what you have to do, if you want to pass arguments to that thread, is put in an extra argument to pthread create, and pthread create will take this argument a, pass it on to myThread. You don't do it yourself. Okay, so that's one thing to keep in mind. So pthread create, just for now, you want to keep in mind that it's going to create thread, it'll allocate stack space, it'll keep track of all the bookkeeping that you need to do to track the progress of the thread and all that. And then it starts running right away. All it'll do is print whatever was passed in, and remember this argument comes from here, and the way pthreads work, those arguments are passed in as arguments to pthread create, not to this function directly. And so you'll be sending a as the argument, you'll cast it as a string, and then you'll print it, and then just return nothing. So pretty much right after you call this method, or sorry, this function pthread create, you will print out an a. And roughly about the same time, it can overlap, but you will also start up another thread and that will print out the b. Okay, so typically what you do is you start up these threads and then you wait for those threads to finish using something like pthread join. That's what we will use. So this just waits for the thread P1 to finish and checks and makes sure that it did actually return no errors, and then you wait for P2 and you're done. So this one process, which starts in main, creates two threads that may execute at the same time, although these are so small, and that's all the code that the thread is doing. Notice that it is calling a function printf, so it needs stack space to do that, and that's why We have to have separate stacks for each thread so that two threads that are calling the same function don't step on each other's feet, things like that. Okay, so this is common. You can have multiple threads. You can set up and create 100 threads in a loop, stuff like that. Um, and they can all be executing the same function if you want. They can be all executing different things if you want. Okay. So these are the kinds of things that could happen. When you run this program and you compile and run it, it turns out that the order in which the A and B get printed is not easily predicted because it depends on all the other things that the CPU is doing and whether the scheduler gets around to scheduling this first thread to run first and does we can't be sure even though this is a really short thread, not much code in it, just calls printf. We can't be sure that A will get printed before B even. Okay, so the ordering of execution, it can change. You can run this program 10 times, maybe 9 times A will be printed first, because what will happen is this is the sequence in time. Main starts, and so it'll print out this message over here, main begin. You create the two threads, P1 and P2, thread 1, thread 2, and then all the main does after this is main doesn't do any of the printing in this function. That's all done by the threads. So it's done doing its job of creating the threads, and then it just sits here and waits. So that's what this step is. So you create thread 1, thread 2, P1, P2. You wait for the first one to finish, and then maybe, or 9 times out of 10, it'll be thread 1 that starts and prints an A. Maybe every once in a while, thread 1 starts but doesn't get to print, but before it gets to print, maybe thread 2 gets created and prints out the B, and then it might thread 1 might get to run. So that's possible. Try it. Run it 10 times. You might see things that are slightly different, but for a short program like this, chances are this is what you will see is you wait for T1, thread 1 runs, it prints A, then you do the join returns, and then you wait for thread 2. In the meantime, thread 2 has started, prints a B, and then you're done with the join when thread 2 returns, and then you print main is done. Okay, so the main takeaway message is it looks like maybe thread 1 should run every time before thread 2, but that's not necessarily the case. Try it. I would say try it yourself. So there are other scenarios that could happen. So you could, for example, create thread 1, and then thread 1 runs, prints the A, and it returns, but then you don't so as soon as you do the pthread create, you might actually create the thread and it might return before you start to execute pthread create for B. Thread 1 might be done. If you have a speedy processor, this is certainly possible. And then you create thread 2 so that in this particular scenario, thread 1 and thread 2 don't actually run at the same time. That's possible. So I'm going to scroll back up. Previously, we started thread 1 and thread 2, you wait. And then thread 1 starts, and then in this case, it finishes, and you print, and then thread 2 starts and prints a B. Then in the next scenario, things are a little bit different in that you'll see the same output, but you might have created thread 1, and it actually starts up and finishes right away, even before you create thread 2. And then thread 2 starts up and finishes up, even before you start waiting for T1, and then you return from thread 1, you wait for T2, and then thread 2 is done. So here's the third example. This is the third scenario is less likely to happen, but you could create thread 1, thread 2, and then thread 2 might run. So it'll print the B. This is, it's maybe 1 time out of 10 this might happen. And you run thread 2, and then you're in main, you're waiting for, you're at this point. You're waiting for thread 1 to finish. It's not done yet, but thread 2 is done. And thread 1 eventually runs for whatever reason, prints an A, and then you're done with this pthread join for P1. So just because a thread finishes doesn't mean that it automatically starts executing this code. No, you still have to execute. In main, you're going to execute code sequentially, line by line, essentially. So even if thread 2 is done, you can't go past here until thread 1 is done. And once thread 1 is done, you get to the join, or the join returns, and then you start waiting for thread 2, but then thread 2 is done already, and so this this join finishes. Even and it has to execute, this join has to execute after this join, even though thread 2 was done earlier. Okay, hope that's pretty straightforward. The main thing to keep in mind is that code in any process or thread just executes sequentially. It doesn't matter what order threads get executed. Code in any single function, any single process is sequential. So what makes multi-threading hard is the fact that we cannot predict how the scheduler and the environment that it's running in, all the other things that are happening, will cause you to switch from one thread to another. And so it turns out this is okay most of the time if there's no shared data. If you do have shared data between the multiple threads and the process, then if all you're doing is reading the shared data, that's fine. And so the one case where multi-threading becomes really hard is when you have multiple threads that may be right to the same shared data. So you can have shared data between the threads, between the threads and the parent process, things like that. And if you are sharing that data, you have to be really careful which thread or process is writing to the data that you share. That's really what makes multi-threading hard. So here's a simple example. I'd encourage you to try this out. So as before, we have pthreads, and then we have, let's say, a .h file containing the header file for some other code. Let's say with the header information for threads. And so we can have a global variable, and we'll go into what volatile means later, but we just an int, and we initialize it to 0. And so here's what the myThread code does. So this is the function that's going to be executed by pthread join. So it's not shown what the pthread will execute this function. It's not shown how to create all that, but it's just like basically like before. Okay, so you use pthread create once again to create 2 threads, and then what each thread will do is just sit in a loop and then add 1 to I, and start at 0, go up to 10 million. Sorry, add 1 to counter. Sorry. So you sit in a loop and add 1 to counter as 10 million times. That's all it does. So what you would expect is that if you have 2 threads running the same piece of code, and all it's doing is essentially sitting in a loop and adding 10 million times to the counter variable, you might say, well, thread 1 will execute, and this for loop is just one big thing, and it'll just do all this work. It'll add 10 million to the counter, and then thread 2 will come along and it will add another 10 million, and you will expect that when you're done with this program with 2 threads, the counter will have the value 20 million. So that's what you would expect. But actually what happens, it turns out if you run this program, you will see this for yourself too, that you will get all kinds of different values, like 19 million, 345,000, so on. Okay, or 19 million something else. You run this 10 times, it's very likely that you will get, very rarely, maybe 20 million, but most of the time you'll get something short of 20 million. You won't get more than 20 million. You'll usually get something, almost always you'll get something 20 million or less. Okay, so, and then the whole thing, the rest of this, basically the rest of this section is figuring out how to fix this, because this is what we really want to happen. We're sitting in a loop, we're adding one to this counter. So here's the problem, is that this counter is shared by both threads, and each thread is actually computing something, and then here's the key thing, is it's writing something to that shared variable. Multiple threads are doing this, and so they could be messing up. That's really what it comes down to. Okay, so here's the problem. The main problem is that this one variable is shared, and we have two things writing, assigning a value to that thread. So a couple of things to know. The static just means that this counter is only visible inside this C file. And the volatile just tells the compiler that the value of this variable can change unexpectedly, so don't use a register. When you write something to it, use the memory location. Otherwise, the compiler will say, I can use a register for this and make it faster. But when you use the, and that would cause problems too. But what we're saying is we're trying to avoid some problems by saying, make this, we're going to mark this as volatile. So make sure to use memory. Do not use don't just keep it in a register and keep looping, because that would surely cause you problems. Okay, so then next up we'll take a look at how to fix this problem of things not adding up.